Good evening, everyone. In the morning, we have learned how to find out the fundamental frequency and the higher resonant frequencies of a string. Right? We got the formula F equals NV by 2N. Right? Where L is length of the string and V is speed of sound, speed of wave on that string. Right? So that's what we have already done. And then we were talking about sound waves in open organ pipe. Right? So I was explaining that just like in a string wave, the particles of the string go up and down, right? And we get an equation of traveling wave like this. Okay, suppose when it's traveling with the right hand side, then just like that we get, instead of displacement, we get an equation of the change in pressure, which is similar, and the graph is also similar. That's what we have already discussed. So once again, making it clear that what happens is that if you draw a graph of the change in pressure, then the graph is like this. What this means is that there are alternate regions of compression where the pressure is high, and then followed by rarefaction where the pressure is less. Right? So here the pressure, change in pressure is negative, that means pressure decreases. So expansion or rarefaction. Then here the pressure increases, delta P is positive. That would mean once again that the pressure is more than the average pressure. So because of that, this is an alternate region, right? There are alternate bands or alternate regions. Compression, expansion, compression, expansion, compression, expansion, and so on. Just like here, when we draw the shape of string for a wave, then some particles have positive displacement, some have negative displacement, some have positive displacement, some have negative displacement. Just like that. Okay. Fine. So now we were talking about pressure nodes and pressure antinodes when we got an interruption, right? So let's continue with that. Okay. So what are pressure nodes? Just like we have nodes on the string when there are standing waves, again nodes are those points which simply don't move. That is because they have amplitude 0. Do you remember this? Nodes are those points that have amplitude 0. Similarly, in case of pressure nodes are those points where delta P is always equal to 0. That is, the pressure at that point never changes. It neither increases nor decreases. Just like on the string, if you have some standing waves, let's say this is one example of standing wave, right? So here you have a node, here you have a node. So the position, the y coordinate of this point will neither go up nor go down. That is, it will neither increase nor decrease. Clear? Because this point always has amplitude 0, it will never move. So it will neither go up nor down. Same thing here. At pressure node, delta P is always 0. The pressure will never increase, never decrease. Is the meaning of pressure node clear? Is the meaning of pressure node clear to everyone? Okay, but obviously we have a question. Where is that pressure node? Okay, we have a question. Where is that pressure node? Let's answer that. Now, again I want you to recollect that this is an open pipe that we are talking about. Open here at both the ends. Now, simple idea, listen to this carefully. It's that this is the end point. Okay, and here is another end. Now, this end point is exposed directly to the atmosphere outside of this pipe. You understand what I'm saying? This point is exposed directly to the atmosphere outside the pipe, right? Obviously, there is an atmosphere outside the pipe. Same thing here. So what happens is, to change, I repeat, to change the pressure at this point, to change, that is either increase or decrease, to change the pressure at this point, you would have to change the atmosphere's pressure, which is impossible, which is not, something within human capabilities. I repeat what I'm saying. This point is the last point. It's open to the atmosphere directly, right? It's not like a part of air here. This part of air is not open to the atmosphere directly. There is air over here, there is air over here also. All this is within the pipe. But this point is exposed directly to the atmosphere. So this point can never have a change in pressure. I repeat, this point can never have a change in pressure. Why so? Because there is air around it which is in the atmosphere. You can't change that air's pressure, right? Can you change atmosphere's pressure? Impossible, right? So that's why listen to this sentence and write it down carefully. It's an important point. Okay? Pressure nodes are formed at open ends of a pipe. Did you understand this sentence? Pressure nodes are formed at open ends of a pipe. Again, why? Because this point is exposed to the atmosphere. You can't change its pressure over there. Impossible. For that, you have to change the pressure of whole atmosphere. You cannot do. Right? So, I repeat. The end points for open ends, right? Open end. This end is open, that end is also open. Right? The open ends are where the pressure nodes are formed. Did you get it? Did you get it or not? Now, as far as diagrams are concerned, or as far as mathematical analysis is concerned, do you realize that this situation is very similar to a string tied at both ends? I'll tell you why. Here we know there is a node, here we know there is a node. Isn't it resembling a string which is fixed or tied at both ends? Yes or no? Do you see similarities? What is it at the right end? Node, node. What is it at the left end? Node and node again. Clear? Do you see the similarities? Yes or no? Okay, nodes at those endpoints. What does that mean? It means all the maths that we have done for a string tied at both ends is also true for open organ pipe. Again, open, that is open at both ends. Alright? Okay, open at both ends. Right? So, let's write it down. Okay, let's write it down. Resonant frequencies for open organ pipe. F is equal to NV by 2L. Everything is same. Everything is same as it was in a string. Okay? Fundamental frequency V by 2L. Is that clear? Fundamental frequency V by 2L. Next, resonant frequency 2V by 2L. Okay, then third one 3V by 2L and so on. Everything clear, everyone? Same formulas as they were for a string tied at both ends. Okay, same formula. Right? Only a very little change of meaning. Very little change of meaning. What do I mean? L. Here L will be length of pipe. Understood? Length of open organ pipe. Clear? Second thing. What is V here? V is speed of sound. V is speed of sound in air. Did you understand? Okay. V is the speed of sound in air. Okay, good question. They were in open organ pipes. Are there antinodes? First of all, let's read this question. What is this question telling you? What is this question telling? What is this sentence telling you? Let's see. It's telling you that pressure nodes are formed. Okay, where are they formed? At open ends of pipe. Okay. So it's simply telling you that pressure nodes are formed at open ends of pipe. Okay, is this sentence telling you that antinodes are not formed? No. Is it telling you that nodes are not formed anywhere else? No. For example, if I would draw the diagrams like I have done it for string very quickly, full speed, right? It's as if I am drawing it for myself. Here we go. So this is the first case, fundamental frequency. It would be like this: node, node, antinode. Clear? Clear or not clear? You might say, sir, where is the string? There is no string. This is like a graph. Let me tell you. This is like a graph of pressure. Graph of what? Graph of pressure. Here the pressure is always equilibrium pressure or average pressure. Here and here. Okay? At this point A, the pressure can rise maximum. So this is antinode. Did you understand? So this is a graph. Remember, there is no string inside. This is just a graphical representation. What would be second case? Have a look. What would be second case? Have a look. Node here, node here. Did you understand? And one node here. How many antinodes are formed? Two antinodes. Where are they? One is here and one is here. Clear? All the rules that we have studied, all the rules that we have studied for string, they are all valid here. Understood? They were, hopefully got the answer to your question. Right? Again, this sentence is only telling you that at open ends, what is formed? At open ends, what is formed? Pressure node. That's it. It's not telling you about anything else. Alright? Okay, fine. Let's go to the next thing. Right? So here also there will be harmonics. Here also there will be overtones. Understood? I hope I don't have to repeat it. Same idea as string tied at both ends. Okay? Right? This can continue for as many as you want to draw. Now, let's go to the closed pipe. Also, let's just write one sentence just in case you might need it somewhere. At open end of pipe, sound wave reflected sound wave has phase change pi compared to incident sound wave. Okay, you see this sentence. Yeah, I know. Okay, is it fine now? Yes. So what have we written? This is same as what we wrote for a string. Do you remember that when an incident wave arrives at a string and this point is fixed, then when it goes back after reflection, it will go like this. Do you remember that, everyone? Okay? It will go inverted, right? That is, there will be a phase change of pi. Same thing here. Basically, it's just that the open end of a pipe, behaves in a very similar way to a fixed point on this string. Did you understand? Just like the endpoints of a fixed string are always node, similarly these are nodes. One more thing, that's just like when a wave reflects from a fixed end, it gets a phase change pi, it becomes inverted. Same thing happens here, that if a sound wave arrives like this, then it will go back inverted. Correct? That's how everything works. Okay, inverted as in what? Inverted as in pressure. Inverted as in pressure. That is, you send a pulse of more pressure, higher pressure. So if it goes towards that side, it will go as high pressure, high pressure, high pressure, high pressure. Fine. But then when it will come back, it will not come back as high pressure. It will come back as low pressure, opposite. That's what this is. It goes in a positive displacement fashion, but comes back in a inverted, that is negative displacement fashion. Just like that, it goes as a high pressure pulse, reaches this end, and comes back as a low pressure pulse, not as a high pressure pulse. That is what this is telling you. Okay, which is practically the same, same behavior as a string wave on a fixed point. Okay, all right. Now with that sentence, this is over. Let's go to the next. Closed pipe. Okay, I'm going to erase this. Closed pipe. So what's a closed pipe? Let's start with that. Resonant frequencies in a closed organ pipe. So what is a closed pipe or closed organ pipe first of all? See, if you guess that a closed organ pipe is closed at both sides, unfortunately you are wrong. Okay, what's a closed pipe? Closed organ pipe means closed at one end and open at the other end. Closed at one end and open at other end. That is called a closed organ pipe. Okay, basically organ pipe has to be open on one side. Only then you can play it. Right? You know these musical instruments like flute, okay, where you have to blow air and it would produce a sound. It has to be open on one side, correct? Only then you can blow air. Do you realize what I am saying? If on both sides it is sealed, where will you blow air from? Okay? So hopefully that made sense to you. So let's say that it is open on left side and closed on the right side. Okay, this is clear to you. Let's say that it is open on left side and closed on right side. Okay, in such a tube, what will happen? Let's see. First of all, when standing waves or when resonant frequencies are there, I hope there is no doubt that here there will be a pressure node. Clear or not clear? I hope that there is no doubt that here there is a pressure node. Why? This is open. Okay, this end is closed. Okay, that much clear that there will be node on this side. Why? Whenever you have open end and standing waves are there, you are going to get a node, pressure node at the open end. That's what we have learned. Right? Okay? I have also explained the same reason. This point is open to atmosphere. You can't increase its pressure, whatever you do. Okay. Fine. What about the closed end? Let's talk about that. So to understand what happens at the closed end, I want you to understand what happens as we, from here, let's say we do something that increases pressure, right? So suppose you push that air, let's say you squeeze it, you try to squeeze it here, so the pressure will increase. So that pressure pulse will go all the way to the last point. I repeat what I am saying. From the left end, from the open end, suppose by doing something, you squeeze the air, right? Let's say there is a piston, suppose. Okay, and you press that piston. What will happen? The pressure will increase, correct or not? Okay or not okay? The pressure will increase. So when you push it forcibly, when you push that piston forcibly, what will it do? It will send a high pressure pulse. It will send a high pressure pulse. Pulse means like a jerk. Okay, just like you can give a wave pulse on a string. Similarly, this is a pressure pulse in air, high pressure pulse. So this high pressure pulse will go all the way till that wall of the closed end, till here. If you think of what happens to the last layer of end, let's say this is the last layer of end. Okay, do you realize that when high pressure pulse arrives, this has nowhere to go? I repeat what I have said. When that high pressure pulse arrives, it's up against the wall already. This part of air is up against the wall. It has nowhere to go. So what will happen? When the high pressure pulse will arise, it will get compressed. Okay, that will get compressed. And then, like a cushion, think about how it occurs for a sponge. You press a sponge, then what will happen? The sponge will push it back, correct or not? You understand what I am saying? So just like that, the high pressure pulse hits the wall. Okay, the high pressure pulse hits the wall, and from there it will apply high pressure back. From that point it will apply the high pressure back. So high pressure pulse hits the wall, and then high pressure pulse is reflected. High pressure pulse hits the wall and high pressure pulse is reflected. This is actually opposite of what happens. This is actually opposite of what happens at open end, right? In fact, this behavior is like this. Then when a string wave arrives and here there is a ring. So what will happen when the wave arrives here? The ring will rise. You understand what I am saying? The ring will rise. Okay? And then because that ring has risen up, when it will try to fall down, that will create another wave that will travel in this direction. Do you remember? Do you remember how a wave is reflected? Ditto the same thing over here. Again, I repeat what I have written here. I just explain it quickly again. It's that you are sending a high pressure pulse, you are increasing the pressure, it goes all the way to the wall, but the last part of the air here, it can't go anywhere, it cannot do anything, it can't move. Why can't it move? It's up against the wall, jagya nothing. Okay? So it will not be able to move at all. So what will happen? It will get compressed. It will get compressed, just like a sponge gets compressed. And then what will it do? It will push that wave pulse back. It will send that wave pulse back. Basically, think about it. Here this is compressed air. Next to it there is other air. So when this will expand back, do you realize that it will compress the neighbor? Think about it. It's like you all are standing in a line. Okay, you all are standing in a line, and one of your friends, okay, next to you, extends their arms. Then don't you think you will have to be squeezed? Okay or not okay? Right? So that is what is going on here. The last part of the air, when it will expand, the neighboring air on this side will get compressed. So that way a compression only occurs with high pressure. Right? The high pressure pulse will start coming back. That is, last will compress second last. Okay, then when the wave will travel forward, the second last will compress third last will compress the previous one. So just like here everything was rising up as the wave comes, and now everything once again rises up when the wave comes back. Similarly, everything was getting compressed as the wave goes, and then everything gets compressed as the wave comes back. So, what this means is that this closed point actually behaves similar to this. I repeat, this closed point actually behaves similar to this, but in pressure waves. Now, do you recollect what was the behavior of this ring? Do you remember that this ring ring would have two waves acting on it and its amplitude would be 2A. Do you remember that? I told you that amplitude of that ring would be 2A. Why? There are two waves over here. Which two? Incident wave like this and reflected wave like this. Both add and they add in same direction. So the total is double. Okay, I want you to recollect this information from your notes. We have mentioned it that this will happen. The ring will get double displacement. Is that okay or not okay? Ring will get double displacement. So the same thing here. At this point, the closed point, we will not have zero change in pressure. That is, we will not have a node. No. At the closed point, we will have double change of pressure, which is actually the maximum possible. So that's why at this closed end, we don't have a node. We have a pressure antinode when we are talking about standing wave. So let's write that. Let's write that it is at closed end of pipe, pressure antinode is formed. Okay, so again this is an important sentence, basic sentence but an important one. Why is that happening? Simple idea. This can't go anywhere. The last part of the air can't go anywhere. So you apply pressure on it, it will get squeezed and it will have high pressure coming back, right? It will send high pressure to you, just like incident wave this way, reflected wave also the same way. So total is double, right? Okay, now with this sentence done, we are ready for diagrams. I am erasing everything on this side. Okay. So now the diagrams. So case 1. Now here we have to be careful. Okay, slightly trickier, not that tough, just a little bit tricky. We have to draw antinode here and we have to draw node here. So first case, which will be of course fundamental frequency. Right? First case will be for fundamental frequency. Happening. This is pipe closed on the right hand side, everyone. Closed on the right hand side. So like I said, node here and antinode should come at this point. Closed end antinode, open end node. It's not a straight line. This is half of a loop. Let me tell you what I've drawn. I have not drawn this. I've drawn half of that. Make sense? Make sense or not? Resonant frequency. I did show you the resonant frequency video yesterday, my friend. On a string we were seeing resonance, weren't we? Do you remember? Can you see air? Devar, I'm going to ask you. Can you see air? Then how will you see air's vibration or air standing waves? So that's the problem. Understood? We can't see air, we can see string. So we did work with string, right? Maybe you might get some animation or something, but like I said, animation isn't real. Okay, if you want to see an actual one, it's not possible. At least it's not that simple because you can't see it. Perhaps by making some smoke screen or something, you could do it. I'll search for it. Right? If someone has done anything like that specifically, right? Anyways, so hopefully you understood how we got this here. Like I said, it's half of this loop. So, do you realize that in this case, we have this length L is equal to lambda by 4. Raise your hand for if you have understood that lambda by 4. Raise your hand if you have understood lambda by 4. Alright, let me just repeat it, it's very important, everyone. See, what we have learned earlier is that when we draw such a loop with node here, and antinode in between, this total length is lambda by 2, isn't it? And now here we are only drawing up to this point, so it's half of it. What is half of lambda by 2? It's lambda by 4. Clear? Okay? Right? So we have drawn half of this, that's why it's only from node to antinode, lambda by 4. Okay, so this is the first case. This is the first case. Now, let's derive frequency. See, we have got L equal to lambda by 4, so lambda equal to 4. Okay? So what is frequency? Frequency of any wave can be written as V by lambda, isn't it? Right? So let's put it here. Understood? So fundamental frequency of what? Closed organ is V by 4L. Is it different from open organ pipe? Is it different from open organ pipe, or is it the same formula? Is it different compared to open organ pipe formula or not? I hope everyone has their formulas with them. The derivation part is same actually, right? Draw the diagram like I said. Draw the diagram. Once you draw the diagram, it's very simple. Just simple F equal to V by lambda and you're done. Right? But the formula is different, isn't it? Here there was a 2. Yes or no? Here there was a 2. Clear? So that's one thing that is different. Right? There are more things that are different. Okay, waiting for you. Let's write down the second case. Second case, that is higher resonant frequency. Remember, higher resonant frequencies are called what? Everyone, higher resonant frequencies are called what? Higher resonant frequencies are called repetition. Come on everyone. Higher resonant frequencies are called, yes, overtones. Over. Think of that. It's very easy to remember. Overtones. Alright, second case. Okay, let's see what's the second case. Again, draw diagrams, don't be lazy. 3 વાર કરશો ને પછી આ બંધ કરીને આવડી જશે. એક્ઝામ માં ભલે ફોર્મ્યુલા ભૂલાઈ જાય, બધું આવડી જશે. So here is a node, here should be antinode. Okay? તો પાછું એ નહીં કરું. This time we will draw it like this. Okay, and excuse me if I get it wrong. There will be one node here and one antinode here. Okay, it will be like this. Now how to do it? Have a look. Did you understand? Yes or no? Yes or no? Basically, the condition should be satisfied. What's the condition? Node here, antinode here. Okay? Node here, antinode here. This was just 1/4 wavelength, isn't it? Or half loop. You understand what I'm saying? If you understand loops. Okay, this was half loop. Here what do we have? Here we have one loop and half loop. So that is, we have it like 1.5 loop. You get what I'm saying? You get what I'm saying? We have 1.5 loop. Okay? This was half loop again. So every time one loop will increase. Every time one loop will increase. Go back to string case. Come on everyone. Go back to string case. Look at the nodes in string case. First one, fundamental, only one loop, isn't it? Second one, 2 loops, 2V by 2L. Yes or no? Third one, 3 loops, 3V by 2L. Did you see that? Everyone, did you see that in your notebook? Did Did you see how loops are increasing in your notebook for string? Same idea here. Same idea here. First case, nothing, just half a loop. Okay, not even one loop, only half. Second case, one loop more. So 1.5. Clear? Diagram is clear? Okay, 1.5 loop. The diagram is like that. You know how I draw it, you know. Sometimes people find it difficult, right? And I am one of the most, worst person when it comes to drawing. My skills are horrible. You could do it like this, okay, like a fish. Done. Nobody can say this is wrong. Understood? Yeah, just be a little careful, don't let it go out of this. Clear? This way you can draw very easy, right? Don't have to worry about R. Okay? Fine. So this is done. Now what's the length here? This length will be equal to, let's think about it carefully. Have a look. Node to node, how much length? Node to node, how much length? Node to node, how much length or how much distance? Come on everyone. Distance between two nodes, consecutive node, lambda by 2, very good. So till here is lambda by 2. This much is lambda by 2. And this is node to antinode, just like this. This is lambda by 4. Clear or not clear? Clear or not clear? Node to antinode. Why? Because this is a half loop. 3 lambda by 4. Is this clear? L is equal to 3 lambda by 4. L is equal to 3 lambda by 4 is clear. Please everyone remember one thing. Some of you might say, sir, how is it possible that here the whole length was lambda by 4 and here only this much length is lambda by 4? Obviously, because we are talking about a different frequency. If frequency will change in the second case, obviously wavelength will also not be the same, right? So in these two cases, frequency is different and wavelength is also different. Understood? Okay, so don't let this confuse you. Don't think that how can this be lambda by 4 if this is lambda by 4? Okay, the wavelengths are not same. In the two cases, the wavelengths are not same. In fact, this wavelength is less than that wavelength. We will see that very soon. Okay, so this is L is 3 lambda by 4. So what is lambda? What is lambda from here? 4L by 3. Look at this. Are the wavelengths same? Look at this. Understood? The wavelengths are not same, obviously, because frequencies are not same, right? So now, what will be this frequency? If lambda is 4L by 3, yes, Riya? Yes, Dikshita correct, Devars correct. अरे वाह, आगे निकल गया हो माना जी, होशियार थे क्या बता? बस आगे काम करता रहो. बराबर ने? आजे मने गई बोलो. Very good everyone, those who have found the final frequency. હવે તો બધા મંડી પડ્યા. કરો માર નથી કરું. નથી કરું. તમે જ કરના. What will be F? Come on everyone. So many of you have done it. Very good. V by lambda. Isn't it? Okay, so V by lambda means V divided by 4L and 3 will come in numerator. So 3V by 4. Right? 3V by 4L. Okay, like many of you have got. Well done. Now, do you see something strange or different at least? In case of strings and for open organ pipes, we are getting NV by 2L. That means 1V by 2L, 2V by 2L, 3V by 2L. But here, do you see there is a jump? Do you see the jump of integer? 1V by 4L and then directly 3V by 4L. Do you see that? 1V by 4L and then directly 3V by 4L. Yes or no? Okay, very good. Right? Fine. I think after this, let's just draw the diagram for the third case quickly and then generalize it. Okay? Let's generalize it, but first we'll draw a diagram for the third case. So, come on, everyone. So, what do we have? 2 loops. Okay. Now my drawing skills are creating trouble. So I'll cheat. 1, 2, 1, 4. Okay, done. Clear? Okay, so 1, 2 and 1, 4. Alright? So in this third case, we have node here, node here, node here, and antinode here. Okay, this is closed in. Alright? Diagram clear? So, what will be L? L will be equal to lambda by 2, and lambda by 4. I hope everyone understood that. That is equal to 5 lambda by 4 by taking LCM. That is equal to 5 lambda by 4. Okay? If L is 5 lambda by 4, then lambda is 4L by 5. Alright? Lambda is 4L by 5. Okay, and we get F is equal to 5V by 4L. You can confirm that yourselves. F is equal to 5V by 4L. Alright? Very good. Okay. So, now general formula. First case we got, okay, here, general formula. First we got 1V by 4L for fundamental, then we got 3V by 4L, and now we have got 5V by 4L. So we see what we are having. 1, 3, 5, odd numbers. Okay or not? 1, 3, 5, odd numbers. After this we will have 7. After this we will have 7V by 4L. So general formula. Okay, last point. Number 4. General formula for resonant frequency. For resonant frequency of closed organ pipe. Okay, general formula of resonant frequency for closed organ pipe. F is equal to odd number into V by 4L. Odd number. Now, how to write odd number? In 10th, you might have studied this. You can write 2n minus 1, you can write 2n plus 1. Do you remember that? You can write 2n minus 1 or you can write 2n plus 1. Correct? But we will choose 2n minus 1. Okay, there is no reason really. Okay, simple idea. If you want to deal with the first case, then you just put n equal to 1. 2 into 1, 2. 2 minus 1, 1. 1V by 4. Okay. Okay or not okay? So I am going to use 2n minus 1. Again, using 2n plus 1 is also correct, but the meaning will change a little bit. You have to be careful if you want to use 2n plus 1. Alright, I will go with 2n minus 1. Okay. So 2n minus 1 V by 4L. When n is integer 1, 2, 3, you can't put 0. You can't put 0 here, right? N will be 1, 2, 3 and so on. Okay, so this is again important formula. So 3 things to remember. Ultimately, out of all this, you should remember at least 3 things. Number 1, resonant frequency for a closed organ pipe. Okay, check this. Then resonant frequency for open organ pipe. What is it? Open organ pipe NV by 2L, isn't it? Resonant frequency for open organ pipe is NV by 2L. And similarly for string also, which is tied at both ends. Right? String tied at both ends. Alright? For that also it's same, and for open organ pipe also it is same. Alright? Then we will talk about the missing things. We will talk about the missing things next time. Alright? So keep this formula in mind. Make sure you remember them along with terms. Alright? So that's it for this class. Goodbye everyone.